Hello, my name is Omneya Sultan. I'm a student in the DSCI 551 morning section, and I'm presenting my one-person project for EDFS. So because this is a one-person project, the implementation is on a Jupyter Notebook. I'm showing you here my Jupyter Notebook that has the user interface using IPyWidget Interact for Python. And I also want to show you that this notebook is right here. It's EDFS UI, Omneya Sultan. It's on my local machine. The other folders that I have are old notebooks, and I have a small data set that I will use later to copy when we're implementing the put function, so that I can show you the put function implementation on the fly as part of the demo. So the first thing I want to walk you through in the implementation is the directory structure table. So this is an implementation of the cat function, and I'm looking at the directory structure table in my EDFS, and I will get back to explaining that in more detail, but mainly I want to show you my file system information tables and walk you through the hierarchy. So my directory structure table has, for each node, what is its parent, what is its child, what's the path to it, and what type of node it is. So I have, from the root, I have a child called data, and I also have a child called file system information. So these are sort of like the data node and name node in HDFS. And then my data node has three children. It has the data set that I used for the implementation of this project, which is called detailed, the first file of this data set. And then it has abridged, .csv, and then it has small data.csv, which I just showed you in my folder. And even though this is just sort of like a test file, the reason why I have it and the reason why it's called small data is because abridged and detailed are a very large file in the order of hundreds of thousands of rows. So implementing the cat function in particular on these large files using Interact and IPyWidgets causes the notebook to crash, because this is obviously a limitation of using Jupyter Notebooks for this kind of implementation. However, it was the required interface for a one-person project. But in order to show you, and also the cat function works if outside of using the Interact function, like if I were to just call the function itself, the cat function, it will work, and it will show the contents of the large data files in a normal Jupyter Notebook without Interact, just a note. But anyways, back to my main point, I'm just explaining here why I have this small data file, which is just a test file for the demonstration purposes. So again, back to walking you through the directory structure table. So as I mentioned, I have these three children for the data node, and then the small data node itself, as a node, has no children. Its parent is data, and this is its path. Similarly, for abridged and detailed, they have no children, and they are files, and these are their paths. And then back to the file system information node, it has three files: directory structure, file metadata, and partition information. And then these are the three nodes listed here with their paths. And the file that we are looking at right now is the directory structure. Now, if I were to cat the file metadata file, now I can see that I have 1, 2, 3, 4, 5, 6, 7 files. I have the directory structure file. This is its file ID, file name, file creation date. I have the file metadata and partition information, and then I have detailed, abridged, and small data. If I were to look for partition information, I would see that I have directory structure, file metadata, and partition information are not partitioned. They are uploaded into the EDFS as one single file because they are small files. And then detailed and abridged, which are significantly large files, have been partitioned to partition 2, partition 1, and now have the same file ID in the partition information metadata table. And similarly, abridged, both partitions have ID 99, and they are partitioned into 2 partitions. And then small data, just for the purposes of the demonstration, and this is something that was uploaded using the put function. These are the partition locations of each partition, and this is the unique file ID for small data. So if I were to further drive this point and allow the user to understand and navigate through the directory structure, I can then use the ls function. So the ls function here in my the interact notebook, you just give it, obviously, as you've seen, you give it a path text input in a text box, and then it automatically updates the result. So here it's the default value for the ls is the root, and this function lists all the files and directories in the directory path that the user provides. So if I were to now go beyond the root, now I can see that I have, under the root, I have data and file system information. So if I were to look at data, I can see that I have detailed, abridged, and small data. And if I were to look at file system information, I can see that I have directory structure, file metadata, and partition information. Now, what if I wanted to make a new directory? So let's say under data, I want to create a new directory called new data 1. Press enter, give it a minute. Now, if I go back to my directory structure table, I'll be able to see that a new node called new data has been created. Its parent is data, it doesn't have any children. This is its path and its directory. And I can also see that another entry has been added for data itself. Now data has a new entry where the child is new data, and again, this is the path. So this is the make directory function, and the way the make directory function operates, it creates a directory in the path specified by the user. So you just enter the path and it creates it, and then it proceeds, after it has created the directory, it proceeds to update the directory structure table to reflect the existence of an additional directory by adding the new entry for the table itself, and also it updates the parent. That now has an extra child directory, and it also does a sanity check, and it confirms that the directory was successfully created by calling the ls function, which we just explained. And if the directory doesn't exist, it doesn't find it in the ls function, then it would give you a message that it actually failed to create the directory. And if the path also does not exist, if the user enters a path that doesn't exist, then the function will raise an exception. And in general, in this notebook, if an exception is raised at any point, the way to get out of that is to rerun the cell. So this is now the make directory function. Now on to the put function. Now let's say I want to put a new file in this new directory that I just created. So I'm going to copy small data and create a file, call it small data copy. And now I want to put this file, and I want to put it in this path. I want to put it under data, new data 1, and small data copy. And then I want to give it the same lower and upper ranges as small data. So the file is small, it has a range, it's from 0 to 30. So I'm going to give us the partitioning for the put function. I'm going to give a lower range from 0 to 15 and an upper range from 15 to 100. And the hash attribute is the number. So just to further explain how the put function works before we actually run it, the function allows you to provide a file, and this file has to be in the same directory as where you're running the notebook. And then you need to give it the path in the EDFS where you want to upload it. In this case, we want to upload it to our new directory that we just created, which is new data 1. And then you give it the attribute that you actually want to hash on. So it could be any integer attribute that you want to hash on that actually exists in the data set that you're uploading. You could use that to partition into two partitions, and then the put function here allows the user to provide the lower and upper ranges of the partitioning that they want to do. So now if I were to press enter in order to load this input and then click the put button and give it a minute. Now, if I were to go to the directory structure table again, refresh. Now I can see that small data copy has been created. Its parent is new data. It doesn't have any children. This is its path. And I can also see that new data itself as a node has new data copy. The new data one, the parent, has been updated as a node. And now it has a child, which is small data copy, because originally it didn't have any children because there was no file. Now, if I wanted to check because I just uploaded a file, now if I wanted to check the partition information, now I can see that in addition to small data, I have small data copy, and these are the partition locations that were created for me by the system. And if I were to check file metadata, I can also see that I have small data copy with ID 35, and this is the file creation date. So now this is the implementation of the put function. Now back to the get partition location function and repartition and cat function, and also an explanation of how these works. So the get partition location, it queries the file system information node, namely the partition location table, to get the partition locations, which we actually just showed, for the user specified file. It then these partition locations are actually MySQL tables. So when we just created the small data copy, and we just saw in the partition information these like sort of gibberish names. These are actually tables in MySQL. Each table contains a portion of this data set in the MySQL database, because it's an emulated file system. So right now here, we go back to reading the partition location. So the partition locations are MySQL tables that were created at the time the file was uploaded into two partitions based on the user's specified partition ranges. So when you get these partition locations, you just query the partition location, the partition information table that I just showed, and then you can see the partitions. So for example, if I wanted to get the partition location of detail, for example, I'll see that these are the partitions. If I wanted to see what are the partition locations of this new file that we just created, I can see the result here, and I can see what are the partition locations. Now, if I wanted to actually read the partition, so let's say I wanted to read this file that we just created. So I'm going to enter here the file. And this is actually the contents of the file. And then if I were to change the toggle to the other partition, then I can see the other partition. Just as a note, the reason why this didn't change is because the small data and small data copy are the same, and it was actually initialized to small data copy. Now, a note on displaying files as pandas data frames in Jupyter Notebooks using Interact. The reason why we're using these small data test files is because, as I explained at the beginning, the abridged and detailed files are very large, so they would cause the Jupyter Notebook to crash. However, if you use all these functions in a notebook without the user interface, they would run fine, no crash would occur. The way that this function operates, the read partition, so now it takes the file input argument and it uses it to call the get partition function, which we just explained. And then it uses the partition names to query the corresponding tables, because as we explained, these are these are tables on MySQL, and to display the contents of the selected partition. If we go back to the cat function itself, so now the cat function is very interesting in that you're giving it an entire file, you're not giving it a partition. So in order to do that, it displays the contents of the file by concatenating the data from all tables that contain partitions of the file. So it actually uses the get partition and read partition functions. And then first it queries and it gets the partition locations, and then it uses these functions, and then it concatenates the output into a single file. And now you can see the contents of a single file here. So that is all of the functions except for remove. So now if I wanted to remove a directory, so let's say I wanted to remove, create a new directory that is empty and remove it. Because if I try to remove this directory that has new data 1 similar to the actual remove function, it will give me an error that the directory is not empty. So let's say I'm going to create a new directory called new data 2. Now, if I go to the directory structure table, I can see that a new node called new data 2 has been created as parents as data, and I can see the data now has a new child called new data 2. Now, if I wanted to remove that directory, I'm sorry, let's say if I wanted to remove, instead of removing a directory, if I wanted to remove a file, let's say I wanted to remove a small data.copy. This will actually also work for directories, but let's try it first with a file, which was the requirement. So, so let's say I wanted to remove this file. And press enter. And it's done. And now if I go back to this table, I will be able to see that the small data copy is gone. And new data 1, which was the directory where new data was created, it now has no children, but it still exists as a child of new data. So that brings us to the end of task 1, and now for task 2 for the search function. Now this search function is very versatile in that it's not hard-coded to a specific file or a specific table in MySQL or to a specific attribute. The user can actually provide any file and provide any search attribute that's an integer and provide a lower and upper range for the search. And then the function will use the Python map function to return the results in that range by using the read partition functions in order to read the partitions and then search through them using the PMR implemented search function. So let's say I wanted to search in our big file, which is detailed. And then I wanted to search on the cost of rides. So detailed is a table that contains transactions of rides in a cab company. So if I want to search for the cost of transactions, and I want to search for all the transactions that were between $90 and $91. And I press enter in order to upload this data, and then I click search. And I can see that 275 records could be found in the specified range in the first partition. And then in the second partition, I can see that 375 records could be found in a specified range in the partition, and these are the records displayed. And that's it. That's the implementation of the EDFS using Interact in Jupyter Notebook. Thank you very much for listening, and take care. Bye.